For those of you who recently received the latest issue of Astronomy Magazine, you can see it there. On the cover of Astronomy Magazine, I just got this this past week, is a story, or at least a picture about a drawing, I should say, of some of the things that TESS is doing. So when you open it up, the main story for this month's astronomy is the work that's being done on this particular mission. And tonight, we're very fortunate to have Ms. Natalia Guerrero, who is the TESS Object of Interest Manager and the MIT TESS Communications Lead in the TESS Science Office at the Massachusetts Institute of Technology in Cambridge, Massachusetts. So she was telling us about all the rain that they're getting this day from the tropical storm that's made its way up there. Prior to the TESS launch in April 2018, she contributed to the pre-flight testing of the 4 TESS cameras. And Natalia studied physics and writing at MIT and graduated in 2014. So we're very happy to have Natalia with us tonight. And Natalia, I'd like to pass it over to you.
Thank you. What a wonderful introduction. Thank you all for having me. I am really excited and honored to be talking to this group, especially because as one Space Coast person to another group of people in a space-oriented city, I feel a little bit of kinship with you all.
Absolutely.
So I'm going to go ahead and get this presentation up and I will share my screen.
Okay, and while you're doing that, I just wanted to remind everybody that if you have any questions, please feel free to post those in the chat function. We'll try to get to those at the end of the presentation tonight. And Natalia told us that there may be some pause points in the presentation tonight, so that that'll give us an opportunity to maybe ask those before she completes the presentation. So use that chat function to ask any questions that you have.
Great, so I'll get started. I work at the TESS Science Office at MIT. Now, TESS is a NASA mission, but it is operated primarily at MIT, which you can see here on the banks of the Charles. I took this picture from the top of the highest building on campus. And actually 2 floors below my feet are the offices of some of the primary exoplanet researchers. But as well as the building that I am standing on top of, I actually work in this little 1970s era 6-story concrete building over there. So that is where the TESS Science Office lives on the campus of MIT if you ever find yourself in Boston. So a little bit more about myself. My training is as a physicist. I studied physics as a student. I was really interested in the direct detection of dark matter. And from there, I took a lot of that experimental knowledge that I had and applied it to the camera testing for TESS. And I'm also interested in science communication. And while I was a student at MIT and for a while after, I also did, I was a DJ on MIT's radio station. So it's a really wonderful university for lots of interests. Since then, I have been working on the TESS mission. I am really interested in how art and science can interact and have worked with artists, vocalists, composers on creating works of art that help scientists extend their understanding of their own work. So I wanted to start with some big questions because I think these are the best way to give the so what of astronomy. I think so often people outside of this world of looking at the stars often say, like, why does this matter? There's so many other things to be focusing on here on Earth. But there's really some fundamental questions that I find very compelling about studying exoplanets. And the first one of those is, how unique is Earth? And so this image was actually taken by one of the astronauts on the Apollo 11 mission on their way back from the moon. And I can just imagine what that astronaut was thinking behind the lens of this camera. I've just been to the moon where it's cold, it's inhospitable, there's no atmosphere, it's hot, it's cold. And then to look at Earth and it's this haven with water, with land, with a thin atmosphere, and it's able to host life. So how unique is Earth? And then taking a step further from that, how unique is our solar system? So we know about the structure of our solar system from the course of study, and solar system objects are some of my favorite objects to spot in my own backyard. So on the inside, we have our set of small rocky planets. As we move further out from the sun, we have the set of gas giants. And then as we move even further out, we have the set of, again, small rocky objects. So this combination of multiple types of planets in this particular dynamical arrangement, we want to know how unique is our solar system. And then I think the most existential question of these all is the big one. Are we alone? How unique is Earth? How unique is our solar system? Where do we fit in the cosmic landscape? And I love studying exoplanets because every day I get to, I guess, grapple with this particular question. So I'll first define what is an exoplanet. It's simply any planet which is outside our solar system. So we have discovered over the course of the last several decades, exoplanets, a few in distant star systems, but also there have been a few cases of discovering exoplanets outside our own galaxy. And so I wanted to first step through a little bit of the history of exoplanets and what they are. So detecting exoplanets is something that has only been around since the mid-early 90s. I took this image of Jupiter in my own backyard. I thought the astrophotographers in this group would appreciate a little bit of astrophotography snuck in here. I took this with a DSLR just set up in a parking lot. And I found this to be a really good way to help myself understand how difficult a detection finding an exoplanet is. So Jupiter is visible in this picture. It's a little blown out, but you can see on either side a couple of its moons. And this is in our own solar system. We're able to resolve across a few pixels the disk of Jupiter and a couple of its moons. Now we have to extend this from a few tens of AU to light years and tens of light years, and think about transits of planets crossing across the face of their star, which is one of the major modes of detection for exoplanets. So this is actually a video of Mercury transiting the sun. So you can see the relative sizes from the point of view of the spacecraft is Mercury is small and the sun is very large. And so with the transit method, which is one of the methods that is used for detecting exoplanets, we have the star, and when a planet crosses in front of its host star, it blocks out a small amount of that star's light. And then as it moves out of the primary transit, it reflects some of that star's light, and then that star dims again when the planet crosses behind the star. And that second dip is much smaller because this is a tiny amount of light relatively. So what does that actually look like? We can map this out as a change in brightness over time. So a small planet will make a small dip, a larger planet will make a larger dip. And of course, this is only for planetary systems where we just so happen to have our line of sight lined up with the orbital plane of this planet. So what kind of stars can we observe exoplanet transits around? So if you look, I have two stars here. On the left, I have a sun-sized star. And for a typical exoplanet, I think this here is approximately 1 Jupiter radius. You can see that the dip here is very shallow and very long. It's a very long duration transit that we would be looking for a planet of this size around a sun-like star. However, if we look around an M-type star, which is a small, cool red star, we are able to see that the comparative surface area ratio is much better for having a nice deep transit with a shorter duration. So this gives you an idea of what kinds of, how star type affects what kind of planets we can detect. And all of these values are in the 1% range. This is 1% or less of the light from that star is blocked by a transiting exoplanet. So this is a very precise measurement that needs a lot of care to make. So we had a few dozen exoplanets discovered by the early 2000s, and then this new space telescope, Kepler, came along, and Kepler looked along a sort of pencil beam, a very small fixed area of the sky, and was trying to conduct a census of all of the stars in that area and find as many exoplanets as possible there. And it was looking for Earth-like planets around sun-like stars. Now, one of the things that Kepler did was it created this huge paradigm shift in the study of exoplanets. We went from dozens of exoplanets, 2000s. Kepler showed us that exoplanets are common, which was something that was not conceived of before that. And it showed us that around M-type stars, which are those small red stars I mentioned before, which are the most common type of stars in our solar system, planets are more likely to form around those stars. So Kepler was able to give us these sort of now common knowledge facts that 10 years prior, we could not have imagined, and it caused the exoplanet field to explode. So from Kepler, we learned about sort of our family tree, our network of relations among exoplanets. So we learned about exoplanets like our own that look kind of like the planets that we have in our own solar system. For example, the gas giants. We have Jupiter, but there are planets that are up to 20 times the size of Jupiter. There are planets that our Jupiter is nice and far and cool and far away from our sun, but there are giant hot Jupiters that have periods of 11 hours, 2 days, these incredibly short period planets that look nothing like our own solar system. And so they're provoking all of these questions of how do these form? What is the dynamical history of these systems? And so all of these questions are now coming out of this census of planets that Kepler made. We also found Neptune-like planets. We found hot Neptunes, which was another case of a planet that's smaller than Neptune that is in this sort of warm region that we don't have an example of that in our own solar system. We found super Earths that were puffy. We found small dense planets like our own Earth, terrestrial sized planets. And so we're beginning to see the menagerie in which the Earth and our planetary siblings belong. So here's an example of an unusual hot Jupiter, for example. So this is Celt 9b, which was actually a ground-based discovery by the Celt team. And you can see this is a disintegrating hot Jupiter, and it has a very unusual orbit. It is orbiting the pole of its very hot, bright star. And so this is one of those unusual discoveries that, again, prompts questions of how did this happen? How did it get into this orientation? We have planets like the GJ 359 system, where this outermost planet in this multi-planet system is an ice giant, and it is in the habitable zone of its host star. But we're finding that the habitable zones of these systems are much closer into their star than our own habitable zone in our solar system because of how small the star is. And so learning about how the scales slide between systems. And then we learned about planets completely foreign to our own conception. So this is what the landscape of LHS 3844b, which was the second planet that came out of the TESS mission, would look like. It has an M-type star as its sun. It has an incredibly short orbit of, I think, half a day. And so it's this roiling lava world. And the period of Mercury is 88 days. And so thinking about half a day and what that does to the surface of this planet is already, it prompts the imagination in all sorts of interesting ways, and also makes us wonder, okay, how did this happen? So I mentioned the habitable zone before. Right now, the habitable zone is loosely defined as the region around a star where a planet's surface could host liquid water. Further out than that, and the water freezes out into ice. Closer, and the planet's not able to hold on to it, it evaporates. So the TRAPPIST-1 system is one of the most well-known systems because it has 3 planets in the habitable zone. And it's a multi-planet system, and it's really interesting because this is it is around one of these M-type stars again. And I mentioned before that the habitable zone is on this sliding scale. And you can see the entirety of this system can fit very comfortably within the orbit of Mercury in our own solar system. And it's thought that some of these exoplanets may even have oceans. So this is going to be a really exciting target. This system and other systems like it that we continue to discover for telescopes that are capable of studying the atmospheres of these planets. So Kepler has just opened up a huge can of worms, and to me, it just adds more and more things that we get to work on. And it's really wonderful that so many other astronomers are flocking to this field because there is so much work to do. So I can pause here, and if there are questions that have come up so far, we can take some of those.
Yeah, Natalia, Don Borg Anderson had asked a question. We're not sure if it's going to come up later in the presentation around citizen science projects with TESS.
Yes, Don,
Okay.
I will definitely mention those.
Okay. That was what we had so far. So we'll go ahead and wait for that one.
Stay tuned. All right. Any others?
David Brown had a question. David, did you want to come off mute and ask?
Sure. I just had a quick question. How are you able to determine if the planets are gas-based or rocky planets?
We are able, with additional measurements using another method called radial velocity, which measures the spectrum of light from the star, we're able to determine the mass of the planet. And with the planet's radius, which you get from the transit method, and its mass, which you get from radial velocity method, you're able to get the density and start to make some educated guesses as to what the composition may be. And then with atmospheric studies of the planet's atmosphere, you're able to start to add more to that picture.
Thank you.
All right, we had one more question, but Natalia, I'll let you get through the next portion of the presentation, and Celso, we've got you on deck.
Sure. All right, so I've talked about how what the landscape right now looks like. So now I want to switch over to how TESS is contributing to this landscape and a little bit about how the TESS mission came together. I do this also because I know that Houston is a big space city, so anything about spacecraft is exciting stuff. So I mentioned, but I've been talking about these M-dwarf stars, and they're a favorite, and there's data to back this up. And this is a map of the solar neighborhood with the sun in the middle, and all of these color-coded points correspond to stellar temperature. So red stars are the M-type stars, and as you get into the white and blue, that is the hot, bright, young stars. And so we can see sort of visually already that M-dwarfs or M-type stars are the most common type of star. And that is true. They account for about 70% of the stars in the solar neighborhood. And so if we're going to be studying planets around those stars, we want to optimize our telescope to be looking at FGK and M stars. So this is the only graph I will be showing in the presentation. But this is something that I think you are all familiar with in terms of the wavelength response of your own detectors. So Kepler was optimized to find Earth-like planets around sun-like stars. So Kepler was sensitive in the spectrum of the sun, which I have here in blue. However, TESS is interested in M-type stars and FGK stars, which are from the 600 to about 1,000 nanometer wavelength range. So the TESS optics were designed specifically to have a filtration here, a hard filter here at about 650 nanometers, and fall off gently into the red and just into the infrared. And that is because TESS is optimized to study these small, cool stars. So a little bit about how the TESS cameras work. TESS is a very small, compact mission. The whole spacecraft stands about the size of a refrigerator. And I find it really interesting that the cameras actually resemble a lot to digital cameras. So we have 4 cameras, and they're arranged such that their fields of view will all stack vertically into a long strip. We have the lens hoods, which shield Earth and Moon scattered light from entering the cameras. And then the lenses and the cameras themselves assemble together and all loaded onto an assembly plate. So here's a cutaway to give you all the gory details of what the cameras look like. So there are 7 lenses here, all shaped so that the wavefronts come in uniformly, and they land on this detector here. And part of the work that I did while I was a camera technician was calibrating what the spacer between the lens assembly and the camera assembly would be, such that we were getting consistent focus across the detector. And we worked with MIT's Lincoln Lab, and they are a great place to geek out if you are really interested in high precision machining, for sure. And so from the detector plane, the images are read out to a set of focal plane electronics. So I wanted to also spend some time talking about the detectors. TESS is designed to last for decades, and so there are no moving parts, there's no moving shutter. The central part of this detector is what is exposed, and then the frames move off to the sides here, and then move off to be recorded on the camera electronics. So this set of sensors are designed to be very deep to catch all of the light and count even very bright saturated objects accurately. And this is at the sacrifice of resolution. We do lose some amount of detail. We're not able to spatially resolve closely spaced targets because one TESS pixel corresponds to 21 arc seconds on the sky. But that's why we rely so heavily on ground-based observers who have the high resolution tools that we can use to complement the TESS data, which can catch all of the light in these very deep depletion pixels. So a little bit about how we tested the TESS cameras, just because I love optics and hardware and playing in the lab. So I figured I would share that joy with all of you. So we used a laser optical array to shine different wavelengths of light from like 650 to about 1,000 nanometers into TESS. And so we have a set of mirrors here that bounce the light finally off of a parabolic mirror that makes the light look like it's coming from infinity. And then we bounce this off of a gimbal array into a vacuum chamber where the camera is sitting. And this camera is kept at space-like conditions such that we can accurately measure the performance as it will happen in space. And so this is an image of what the fiber optics look like. This is our set of artificial stars, nice and grid-like for us to study. So the cameras would be loaded into a harness and then put into the vacuum chamber. And you can see, I mentioned that 650 nanometer cutoff earlier. And you can see here that there is indeed a blue-green filter to keep light before that wavelength from entering. And so we would seal up this vacuum chamber. Here's a photo of two of the technicians that worked in the clean room. And every time we put the camera in, after a vibration test at Lincoln Lab to make sure it would survive launch, or after a thermal test, we would put a pinhole over the window of the vacuum chamber and take an image at room temperature. The TESS cameras are unique because they can operate at room temperature. They're a little bit noisier, but it's really useful for testing. But they do work best at that sort of -75 level. So these pinhole images often would just be a test image of whatever was in the lab or just dark. But sometimes we would use them, we would use test subjects for very scientific purposes. Here is a picture that we took in the lab with one of the engineering units of the camera. This is myself and 3 other TESS scientists. I really like this picture because I think it summarizes all of TESS science in one image with 4 people. From left to right, Diana Dragomir is at UNM studying long period exoplanets. Jen Burt is at JPL, and she's an expert on high precision radial velocity. Here's me. And then Elizabeth Newton is a professor at Dartmouth, and she works on stellar activity and exoplanets around young stars. So there's a lot of science in this one picture. So after the TESS cameras concluded testing in late 2017, they were shipped to Orbital ATK, which is now part of Northrop Grumman, and they were put onto the camera plate and then wrapped up and put on top of the spacecraft. And you can see here the curved dish of the S-band and K-band that is sent back, and that is what we use to transmit data from TESS. And TESS was turned on its side for additional optical testing. Again, the little green eye winking out. And TESS also spread its wings, as it were. TESS gets all of its power from solar panels, and so those deployed after launch. And so here you can see a solar panel deploy test going on. So TESS was launched on a Falcon 9 rocket. You can see it perched here on the fairing, and the rocket itself is gigantic. This can fit a school bus in it, about. And this was at Cape Canaveral, and this for me was a big moment because I grew up watching shuttle launches from my hometown. And so it was amazing to come back for work and to see TESS all ready to go on the launch pad. And then on April 18th, 2018, TESS lifted off and went into orbit. And this was a hugely emotional moment for myself and for the whole team. TESS was from start to finish. It took about 10 years to get it from the drawing board to the launch pad. So this was really already very meaningful. So TESS now orbits the Earth in about a 13.7-day orbit. It's kept sort of locked in that orbit by the moon, and it turns around once every 2 weeks and beams data back to Earth in a couple of contacts with the Deep Space Network. And so TESS looks at one patch of the sky for 2 orbits, or for about a month apiece. And you can check on how TESS is doing every time it has a contact. The Deep Space Network streams all of the information about who's talking when. And so TESS is here right now. That day it was making contact with Madrid. So a little bit more about the TESS field of view and how it actually takes images of the night sky. Here you can see one of the TESS cameras. It covers 24 by 24 degrees on the sky. And we have 4 cameras, so they all stack on top of each other to make a 24 by 96 strip on the sky. And we have a stare and step observing method where we're staring at just this for 2 orbits, or about 27 days. And so TESS, when it started observing in August of 2018, it started in the south and then continued around in 13 sectors in the south, and then turned around, observed the northern hemisphere. And we just concluded observing the southern hemisphere again in our 3rd year. And now we're going to turn around and look at part of the north again and part of the ecliptic plane. You can see these circles highlighted in red. This is where all of the sectors overlap. And so we get almost an entire year of observations in those areas, which we call continuous viewing zones. So you can get a really long baseline in those areas. And it's very exciting to line that data up now that we have a 3rd year of observations and look at those targets a year later. Also, for reference, we usually look at a TESS sector when that sector is directly overhead from the ground. So some of the targets, as the data comes out about a month later, are starting to set. So we kind of have to hurry up when it comes to follow-up. So this is an old classic, the HA ray, and the constellation Orion fits nicely within about 24 degrees. And if you've shown those who are new to star hopping how to get 25 degrees, you know, thumb to pinky. And so whenever I go out and do that on the sky, I always realize, like, wow, TESS is able to capture these humongous images, these huge parts of this night sky. So this is just a fun brain break of enjoying the TESS images. And NASA has these up on their Goddard website for anyone to download. So if you just drill in, you can see how many stars there are. And there's millions in each sector that we can observe. All right, so I mentioned Kepler measured this like very small area on the sky. And so now TESS is mapping nearly the entire sky. So Kepler and its follow-on K2 observed the part of the northern hemisphere and the ecliptic plane. TESS in its 1st and 2nd year observed both these overlapping regions, and it is going to, starting in September, start observing part of the ecliptic, which is going to be very exciting for getting a second look at some planets discovered by K2. All right. So this is what those images all stacked together look like. TESS observed 70% of the night sky in 2 years. And by the end of next year, by next summer, we hope to have observed 88% or so of the night sky. And I love this image because it's so amazing to see how TESS over time just filled in this part of the night sky. So this is another good time to pause and check in on any questions that have come up.
Certainly, Natalia. We've got a lot of them starting to come in, so
Great.
We'll get to a couple of them here and then save the rest for the next break. Celsa, do you want to come off mute and ask your question?
Sure. Well, my question is in regards, what's the commonality among the stars that have exoplanets? Have you noticed a pattern which ones have exoplanets?
That's a really interesting question because exoplanet demographics is this field that has only emerged in like the last 5 to 10 years because we now finally have enough planets to draw patterns from. And the biggest pattern is that planets form very commonly around small red stars. And that's, I think, like the big, exciting sort of rule of thumb. And from there on, I'm a little bit fuzzier on some of the patterns folks have started to put together. But it is a really exciting field to start to follow.
Thanks for the question, Zelsa. And then Hyde, Wen had a question as well. Hyde, do you want to come off mute and ask?
Sure, thanks, Joe.
Sure.
Hey, the question I have is, of all the stars that's been surveyed, what's the percentage of them have exoplanets?
That is a good question. So we are pretty fussy about, so we have a test magnitude, which I think roughly corresponds to V band. And so in our own pipelines, we don't process stars fainter than about 13.5, but TESS can measure light from targets down to like 2022, TMAC 2022. So we're missing out on like the distant, more faint stars, but we're looking within however many stars are within like the 300 light year mark. And but I don't have like hard numbers on how many of those stars have been yielding exoplanets. The rough count is like we have several million stars that we've analyzed, and we have about 4,000 candidates.
Wonderful.
Cool, thank you.
And then last question, just because I think Bill Spitzeri had a question about one of the slides you had presented prior. So before we get too far from that, Bill, did you want to come off mute and ask your question?
Yes, thank you. Earlier, you showed a graph that compared the wavelengths that TESS and Kepler looked at. And what is the vertical axis on that? What does that represent?
That's normalized more or less to just efficiency.
Efficiency of what?
The detector response. So how good it is at counting, or I forget exactly what the silicon response is, but getting electrons from those wavelengths.
Photon capture efficiency.
Yes.
Various wavelengths then.
Yes.
Okay, very good. Thank you.
Okay, well, we'll continue to queue those questions, and yeah, we've got 3 already, so we'll get to those at the next break. Thanks.
Great. All right, I realize I need to reshare my screen because I have some sound samples that I'm going to play. This is a little bit of a spoiler alert. All right, there we go. So now we've talked about TESS, what it's doing, and so I wanted to also dive into the data analysis because, as any good backyard astronomer knows, that's half the battle, is once you've taken your images, what to do with them. So little recap, we looked at this plot of brightness over time of small planets, large planets. We can see there's this dip that happens when a planet transits its host star. Now, in reality, it's a little bit messier. So here, this is one measurement per point, and this is the axis in time. And then this is normalized to relative flux from the star. So here we have our star in this animation, and here is our itty bitty planet. So if I get this going, we can see the star's flux, and then as the planet begins to transit, it dips. And then as it comes out of the transit, we go back to our original flux level. So TESS is really wonderful, but it has the advantage of being in space. We don't have to deal with weather, sky, anything, and can take continuous observations for 2 periods of 13.7 days. And so we have this wonderful long baseline to go from. So going back to one of the TESS full frame images, I am going to grab a star and I'm going to look at how it changes over time. So this is with the white being assigned to the highest number of pixels and then going down into the grayscale from there. If I draw an aperture and optimize this for sort of the best aperture, capturing most of the pixel response function from that particular star, and plot that over time, I get this raw light curve of flux on the y-axis and time in days on the x-axis. And we can see here that we have this gap where TESS turns around, downlinks the data. We're not taking science images then. We have several outliers. This is from the spacecraft motion, from a little bit of like temperature fluctuations, some jarring in the pointing, things like that. And then a sort of underlying pattern that could be from the star. So we fit all of that out, mask outliers, and come out with a cleaned up flattened light curve, which we can then throw algorithms at to recognize transit-like shapes and to find out the phase, the frequency of those transits. And we are able to throw CPUs, GPUs, machine learning at this to come out with a estimated period for this planet. We're able to phase fold this, stack all of those transits on top of each other, fit a model for a transit shape to it, come out with the transit depth that we estimate for this system. And from that, we can back out, knowing the star's radius, what the planet radius will be. Knowing the period, we can back out the planet distance from its host star, assuming a circular orbit, and start to put together for ourselves a picture of what this planet roughly may look like. So going from pixels to light curves to, with additional measurements of mass of atmosphere, a good picture in our minds of what this planet may actually look like. So I figured we could do a little bit of this ourselves. I pulled out some totally randomly selected TESS images and light curves. So this is, again, what the star looks like in the TESS data, white being the highest value of electrons per second, and then this X and Y here is just what the pixel grid is. So I have my best aperture selected for this target, and I have the flux over time for this orbit plotted here. And I've also gone ahead and, using a Python package called Astronify, made a sonification of this light curve. So we can hear how the light changes. I've assigned the pitch or the note to how much light there is. And so it'll go up and down accordingly. So we're seeing and hearing this periodic strong change in the light. If we look at the y-axis, we can see that this is actually not that much compared to the overall flux. This is well within the less than 1% range I said. So if we ask ourselves, is this an exoplanet? The answer is yes. This is Kepler 12b, which is a 4-day exoplanet, a hot Jupiter that was found by the Kepler mission and reobserved with TESS. So this is a very short version of the process that we go through with the team that I manage, where we're looking at millions of light curves, cutting them down with machine learning, and then with human eyes trained to see transits, taking just a few hundred light curves and pulling out candidates from each sector from those for our catalog. So here's another example. Here we have our planet, or our star. It has a couple of nearby stars. You can see these others. And so this is our best aperture for this target. And this is the flux over time. You can hear it as well. So give people a minute. Thumbs up, thumbs down, yes or no? Do we think this is an exoplanet? I see a thumbs up, see a thumbs down. All right, let's see. This is not an exoplanet. This is stellar variability. So this has a much more diffuse sinusoidal light curve pattern. And you can see there's actually a flare here from the star having an outburst. And so seeing these kinds of pulsations is actually another use for the TESS data is astroseismology, or how stellar dynamics works. And so this is this whole other subfield that is really, really interesting, of understanding the heartbeat of a star. So here we have another, and I'll get right to the sound sample as well. All right, so what do we think? Yes or no? Thumbs up, thumbs down? I see a couple thumbs up. All right, lots of thumbs up. And you are right. This is exoplanet TOI 432b. This is an artist cartoon of this planet and how big it is compared to Earth. This is another hot Jupiter, and with another short period. And so this is another type of exoplanet that TESS is really good at finding because it fits nicely within the baseline of our data. So I wanted to take a little detour and talk about how we name these exoplanets, because the name TOI 432b doesn't really stick in your head. And so TESS objects of interest, or TOIs, are what we call planet candidates that we would like the community to follow up, either to rule out or to confirm as exoplanets a little bit more happily. And so the first planet discovered in a system is planet B, because the star is capital A. So we have numbered these, and right now we are in the 4,000s for number of candidates discovered. So I wanted to zoom out again and talk about the big picture of how this catalog of exoplanets is contributing to our knowledge so far of transiting exoplanets in our solar system. So we have over 3,000 transiting planets, primarily from Kepler, which is this big yellow blob up here in the north, and also from K2, Celt, other missions that I have also mentioned. So this is already a huge number of planets and has contributed so much to our understanding of how exoplanets form and where and what kinds of stars they form around. However, TESS has started to contribute a spatially distributed sample of stars in our solar neighborhood that are bright and easily observable from the ground. So in the first year, TESS observed and found about 1,200 exoplanet candidates. We added almost 1,000 in our second year. And in our third year of observation in the south, we have found an additional 1,200 in doing additional reprocessing of the original year 1 and year 2 data, including looking at fainter stars and for lower signal to noise objects. We were able to add an additional almost 700 targets. So the count as of this afternoon was 4,198 TESS planet candidates. Of course, some of those are going to be duds. We've found about 600 that are false positives, but that still leaves plenty of exoplanets to go around for the community to follow up and observe. And we are finding that Earth is among thousands of exoplanets all across the night sky. And I'm very excited for TESS to start filling in the gaps here in the ecliptic and also in the north, and finding even more exoplanets. A couple of notable exoplanets. In 2020, a paper came out about the TOI 700 system. This was actually led by 2 graduate students, which is indicative of how easy it is to make high impact contributions early on in your career in exoplanets, because the field is growing so quickly and there's a lot of high impact work to be done. And this was the first habitable zone Earth-sized exoplanet TESS found. It's the 3rd planet in a 3-planet system, and it resides in the habitable zone of its small red host star. So this was a really exciting discovery. We've also found planets around violent young flaring stars. So this is AU microscopy B, and you can see that it has a lot of activity, and then the planet just zooms by in this animation. And we were able to catch one transit of it, this planet that is likely disintegrating in the close orbit of its host star. You can see here how we had to fit out all of the stellar flares to grab this little transit. And this is one of my favorite exoplanets as well, because NASA JPL is well known for creating these beautiful posters, and they created this Galaxy of Horrors poster of AU Mic and its Flares of Fury, this ill-tempered star and how it's just peeling away the outer layers of this exoplanet. So you're able to get this, download it, print it, do whatever you want. This is a really wonderful thing. And I was able to contribute it to some of the creative design of this. And it was a very fun process. TESS has also contributed, I mentioned astroseismology, but to other astrophysics, including finding this system of 6 stars all gravitationally bounded together. We have 3 pairs of binaries. These 2 are coupled together and then coupled together in this much larger orbit. And this is what the light curve looked like. And I actually remember looking at this light curve and saying, what the heck is that? And I was very excited to see this paper get proposed and then written, because this is such a fascinating system and you can really get lost in these transits, learning about how this sort of dynamics comes to be. TESS is also able to contribute to transient astronomy. So supernovae, when they happen and we're observing them from Earth, we can see the turn on, the bright flash when everything sort of explodes. But seeing the moments before is really important to understanding what's going on inside the star, inside the body before it happens. So supernovae are one example of what TESS has captured, but it's also been able to capture events like active galactic nuclei interacting with matter around them. So this is an example of this Assassin ground-based survey. Assassin, what is it? 14KO, this object where you have this massive star that is hurtling around its black hole AGN center and getting matter torn away, huge flash of light as it gets too close for comfort. And you can see this huge flare of light. This is also visible in other wavelengths. The Swift telescope was able to observe this. And what's nice is that this is predictable. So TESS was able to observe one of these flares and contribute to a multi-wavelength observation of this occurrence and contribute to this type of astrophysics that has nothing to do with exoplanets, but is still this really valuable time-lapse movie, essentially, of the night sky that TESS creates. So going back to that original question that I asked way in the beginning, are we alone? The answer that I would say after working with the TESS data, finding planet candidates, seeing these candidates get studied, written up, and added to our catalog of exoplanets, I would say not really. And with that, I will wrap up. To answer the question about public outreach and community science, Planet Hunters TESS is a project run by a graduate student and at the University of Oxford in partnership with Zooniverse. And so you can identify TESS transits, mark if you think that there are planet candidates, and real TESS discoveries have come out of this. So several planets have been written up into papers from Planet Hunters contributions. Also, if your telescope is able to if you're confident that your telescope can make measurements of the night sky that can help with photometric follow-up of TESS, subgroup 1 of the TESS follow-up observing program is always looking for new members, and you can go here, tess.mit.edu/follow-up, and learn more about what the requirements are for that. But with that, I will pause again and thank you all for your attention, and I can take any questions.
Natalia, that's absolutely fascinating. Thank you so much for sharing that with us. And, you know, as a club, we're fortunate we have an observatory and a dark site just west of Houston. And there's a lot of science that's being done out there. So for those of you who have observatories in the means, please consider contributing to this particular effort. So we did have a question from Pradeep. He doesn't have a microphone, so I'll ask on his behalf. He says, of the 2 radial and transit methods, which one is preferred and why? Well, I think we know which one the TESS mission prefers, right?
They're complementary, and radial velocity was kind of the heavyweight champion of planet discovery before technology evolved to the point where transits were viable. Kepler was around the first time where CCDs really had the precision and the depth required to make these high precision transit measurements. And before that, radial velocity could be done with spectrographs on big telescopes from the ground. And we've continued to do that and build new telescopes with really powerful spectrographs that can do this precision radial velocity measurements. And that can give you a lot of information about the mass of the planet, the dynamics of the system. And in fact, the first TESS exoplanet was initially a system, Pi Mensa, that we knew about this highly elliptical planet that had about a 5-6 year orbit, very elliptical, very off-axis orbit, but then this star was a very bright star. So Chelsea Huang, the postdoc who was working on this, took a look at it again when inspecting the TESS data for the first time. And she found this incredibly short period planet orbiting in a circular orbit around this star that we already knew had another planet. And the story of this system continues to evolve because there's so many questions about why do you have a planet with this teeny tiny orbit and then another planet with this 5-year orbit? And so that's an example where RV and transit measurements work together to give you a fuller picture of a given system.
Excellent. Thank you for the answer. Don Selly, I think you may have just answered this question as well, but Don, did you want to ask your question about the camera types?
Yeah, really, it's a question of the sensor. Is it actually a CCD sensor or a CMOS sensor? And
It's
then
a CCD.
Is it a CCD? Okay.
Back illuminated.
Yep. Okay. In astrophotography, we're making a big change over to CMOS right now, so that's why I asked. The other follow-on question, if you don't mind, if you had to say what size telescope would be best for follow-up observations, how big a telescope do we need?
Oh, that's a good question. I am not sure. The person to ask there would be Karen Collins. Her name is on that website that I linked, the TESS.MIT follow-up. She is the overlord of all of the ground-based photometric follow-up.
Okay, I appreciate that. I know where the website is. I'll ask that question of her.
Great, thanks, Don. Going from Don to Don Borg Anderson. Don, do you want to come off mute and ask your question? She might not be able to do that. I know she was.
No, I got
oh, there
it.
you are. Okay.
Yeah, there I am. Does TESS work in connection with the European Chaops, which is characterizing exoplanet satellite?
Yes.
It does. Okay. Well, how is that working out? Because it actually is based on discovering, it works a different way. Can you explain how they collaborate together?
Yes.
Yeah.
I'd be happy to.
Okay.
So the Chaops mission is launched while TESS was getting started with its observations, I think in like 2019.
Okay.
And we actually have a Chaops person working with us on the TESS mission because once TESS has published a new set of planet candidates, Chaops can go through and say, okay, which ones are in our field of view? Which ones can we observe? Which ones are really promising to have additional exoplanets? Because Chaops can just sit on a target. And if it knows when it's going to transit, it can get the full beautiful picture of the ingress and the egress of the transit. And so Chaops has contributed to a number of recent publications where it's able to not only confirm planets that TESS has found, but also in multi-planet systems, it's able to find additional planets in the system that TESS wasn't able to observe. So it's great. We love Chaops.
Yeah. Wow, that is fantastic. And sorry I mispronounced that. I'm very.
No, I wouldn't know either. Unless someone told me.
Piston and air quality doesn't go together. But thank you for that wonderful presentation, by the way.
Thank you.
Great. Thanks for the question, Don. And we'll go to Peggy Mueller next. Peggy, I think you had 2 questions that you'd asked.
Yes, thank you also for such an excellent presentation, so much information. And I have worked with planet hunters for a while, and it's a lot of fun. But my first question is, when I was looking at your light curve for TOI 432b, it looked like the dips and flux were variable depths.
Yes.
What would cause that?
So in that particular light curve, I hadn't cleaned it up for like stellar behavior. So it could be that those go away a little bit. Sometimes though, when you get like a big difference in depth, it's because it's actually two stars orbiting each other, and the different radii will give you those changes in depth. But for that, it could just be the scatter in the data. I'm not super sure for that particular system though.
Oh, okay, thanks. And second, so you were talking about the Assassin 14 star that has lots of flares. So if there was an exoplanet within, quote, a habitable zone around that particular type of star, would you expect life to maybe not have a great chance of existing there?
Yeah. So that system was, maybe I didn't mention it, but it's that's actually like a black hole and a big star, and that's what that is. But TESS has confirmed examples of systems, I can't remember the name now, but of multi-planet systems around incredibly active host stars. And for those, we were suspicious, and like actually 55 Cancri is one of those systems where it would be so nice if it had an exoplanet because it's so close. Or is it that one? No, it's Alpha Centauri. I'm sorry. Where it would be so convenient because it's the closest star system to us. But Alpha Centauri is such a badly behaved star that the planets orbiting it have a very low chance, are just barraged by radiation. So if life is there, it's going to look very different from life here on Earth.
Okay, thank you.
Okay, Natalia, do you have time for maybe 3 more questions, if that's okay?
Sure.
Okay.
Yeah, absolutely.
So Bill Spitzeri had asked a similar question. Bill, you asked about the light curve not being, or having a consistent reduction in light. Was that just answered there?
No, I don't think so.
Okay.
Correct me if I'm wrong. You showed us several light curves that shows the transits. The first one, you can see the transits very obviously, but the overall light from the star was constantly diminished. Do you know what caused that, please?
Yes. Actually, now that I think of it, that data was taken with the Kepler mission. And actually it was with Kepler, and Kepler had a very unique way of pointing the telescope where it would roll every so often. And so the star would move slowly across the detector and have this very predictable drift. And so it would look like, because your aperture is fixed, we don't have a dynamic aperture that's following the star, like the light is decreasing because the star is escaping from your aperture.
So Kepler is an old-fashioned transit detector. Okay.
It was doing its best when a couple of its reaction wheels went out.
Yeah, and a short time ago it was the future, and now we're moving forward.
Oh yeah.
Okay, thank you.
Yeah, the future is always a moving target. So we've got Earl, then David Brown, and then we'll wrap up with a last question from Celsa. So Earl, do you want to come off of mute and ask your question of Natalia?
Sure, I had actually 2 questions. One is, since we can only see planets on our plane of vision, has any thought been given to estimating if we can see 4,000 planets in our plane of vision, how many more are we missing? And my second question has to do with Webb. Will Webb, once it's launched, help in exoplanet research?
Yes to both of these. Great questions. So to answer your first question, the transit method, yeah, I don't remember exactly what fraction transit method is expected, but it's a very small fraction of the overall number of stars. So we expect that there are billions of exoplanets in our galaxy alone. And other methods of observation don't require that alignment of the plane of the orbit with our line of sight, like radial velocity, for example, doesn't care. Direct imaging doesn't care. So other methods, and as telescopes evolve to use those methods more powerfully, can give us a broader picture of all orientations of orbits. And then your second question about Webb is also great because the James Webb Space Telescope is going to have a lot of different applications, but one that we're very excited about is its capacity to study exoplanet atmospheres. And I actually have a little animation of how that will work. So here is the James Webb Space Telescope. Let me get this started. And so when a star's light passes through the atmosphere of a star. Some of the light is absorbed, and we're able to measure the spectrum of that light with James Webb. And so you're hoping that the fingerprints of that spectrum of light from being absorbed by carbon dioxide, water, the ingredients for life that we really like. For example, if we want water, if it doesn't have carbon dioxide, if it has methane, which is another possible biosignature, light passing through the atmosphere of that star. Whoops. This is a little bit too in depth. There we go. This one. Sorry, that was the wrong animation. This is how it's going to measure those absorbed wavelengths of light. Is the light will come into the James Webb Space Telescope, and we'll be able to put together a better fingerprint of what elements are in the atmosphere of that star. And right now we can do that with Hubble. We can put together that sort of thing. We were able to do a little bit with Spitzer, but the Spitzer telescope has retired. So Webb is going to be a really exciting space telescope because we can get these more detailed pictures of a selection of targets. And so TESS is kind of a scout mission for Webb. So fingers crossed.
There we go. All right, David Brown had a question as well. Pretty interesting question. David, do you want to come off mute and ask your question?
Sure. Thank you again for the interesting presentation. I was curious if there are any objects which are problematic for your detection methods, such as I was thinking like pulsars, variable stars, oddities like that are constantly changing, and whether they throw off your detections.
Yes.
Or prevent them entirely.
Yes. So variable stars, for example, because heartbeat stars, for example, have this sort of very regular pattern, sometimes our algorithms will trigger off of those thinking like, oh, hey, the down in this sort of EKG-like signature, oh, this looks like a transit. This is a planet, right? And that's why we need a team of people with experience to say, no, computer, that is in fact not an exoplanet. So that false positive removal in the pipeline is where machine learning will really come in handy, and is already coming in handy, where we're able to train the tool to say, okay, this is variability, this is transit-like. But yes, those things come up all the time, and we have to, and they also hamper follow-up, because even if you do find an exoplanet transit, if it's around a very active star, it makes it much harder to do follow-up and pick out that transit from the underlying variability.
Excellent. Okay. And Celsa, you had asked the question. I think we got to some of it towards the latter part of the presentation, but did you want to ask the question anyway?
Well, if she can extend a little bit on the takeaways on keep studying exoplanets, even though if they don't reveal Earth-like life, but still, what will be the takeaway from exoplanets, even if they don't show Earth-like life?
I think that's a really good question. And it's a question we often have to ask ourselves in order to keep going, because we're still sort of picking apart the picture of how our own solar system came together. And to me, that's a very interesting question, because the more systems we find that don't look anything like our solar system, or the more systems we find where we have, hopefully one day we'll find a perfect Earth twin, sun-like star, 365 days away, small terrestrial planet, and we'll be able to study it with telescopes that at that point are able to study it in great detail. And if we don't find life there, I think that's as interesting, because then we have to say, okay, what is it about, I don't know, the element abundance, the dynamics of this planet, the magnetism? We'll be able to start to, it's another puzzle. And I think that's interesting to answer questions about our own system, about, okay, what's special about this system, and how does that help us understand where we belong? And so filling in the family picture, I think, helps us realize, like, how are we similar to other planets? How are we different?
Great. And I lied to you. I said Celsa's would be the last question. We got one question in from Facebook, which I hope you don't mind me throwing that curveball there.
Sure,
but Carl Dunn had asked, And I thought this was a great question. Which exoplanet discovery is the most interesting for you?
I would have to say, let's see. Oh, that's a hard one because they're all so neat for various reasons. I think I am most excited right now. I won't say it's my favorite of all time, but I think I'm most excited right now about the prospect of studying, let's see, oh, it's tough. I would say there's a really unusual type of star called a white dwarf. That's sort of a planet at the end of it, or a star at the end of its life. It's collapsed, it's burned away most of its outer material. And it's very, very small and very, very dense. And you would expect after all of the tumult of blowing off its outer layers that it would have no planets left if it had planets. But last year, there was a paper published by Andrew Vandenberg about this giant hot Jupiter orbiting very close into one of these white dwarfs. And to me, that's like a riddle of how did this happen? How did this get here? And so I think that's, for me, a really good representation of why this field is so cool, because every time we look at a new set of data, we're realizing, oh, there's even more unique systems out there.
Excellent.
Yeah, thanks for that question.
No, I appreciate you answering that. You know, we had a Texas Star Party virtually last month, and when we were interviewing certain folks, like you know, famous comet discoverers like David Levy, we'd ask questions about, you know, which of these observations or discoveries was your favorite. The answer is always, you know, you're trying to ask me to pick the favorite of my children, right? So it's a little difficult, but I appreciate you taking a stab at that, and certainly that's interesting. Natalia, thank you so much for joining us tonight. This was a fantastic presentation. I'm just absolutely fascinated by it, and I can't wait to actually jump in and help contribute to this program and a lot of the science that you all are doing. So I really appreciate you. And where can people keep up with your work?
So I am on Twitter. I put up my Twitter handle, I think, on some of the slides. I am Sleepless at MIT. In terms of like the gory details of how the TESS exoplanet catalog works, I recently published the mission paper for TESS on the TESS Objects of Interest catalog. I can give you the link to that paper here. It's online, freely accessible. And the next time I publish a paper, it will show up there.
Perfect. Well, we look forward to, you know, keeping track of everything that you're doing. We wish you all the success in the world. We're glad you could spend some time with us today, and we hope that you can come back and visit us sometime in the future. So really appreciate your time today, and really excited about all the work that you're doing. So thank you so much.
Great. Thank you for having me.
Absolutely. And for everybody else who joined us tonight, thank you. I think this was a wonderful treat, and I'm just giddy as can be to learn more about this. So our next meeting will be Friday, August 6th for our general meeting. The novice meeting will be the Thursday prior to that. If you're on social media, please follow us on those different locations that you see there. If you have any questions, email us, info@astronomyhouston.org. I'd love to answer any questions that you have. And I'll do my best, Natalia, to pass on all the information that you have here, including links to your social profiles and whatnot, so that we can keep count of your successes. And again, thank you very much. And we wish you all the success in the world. And please come back to visit us in the future.
Of course. Thank you all.